Come back to our YouTube channel. So still talk about the damped harmonic motion. Damped harmonic motion is a type of harmonic motion whereby the amplitude of the vibrating body decreases gradually due to energy which is continually dissipated. So we all know in practice the amplitude of a vibrating body does not remain constant, so it progressively becomes smaller. So that's a damped harmonic motion. For a damped harmonic motion, our damping force is directly proportional to the velocity of the oscillating body, and is given by this expression here, which we call our equation 1. So this is the expression for our damping force. So if we have our damping force F of D proportional to our velocity, if we remove the proportionality sign, we introduce our damping force constant, which is B. Now you will notice that there is a negative sign here in equation 1. It is because whenever our body is moving in this direction, our damping force always acts in this direction. Similarly, if the body is moving in this direction, our damping force acts in this direction. So they are always opposite in practice. So we have two forces acting on the body. This includes our damping force and our restoring force. So our restoring force is given by this expression, which is negative kx by Hooke's law, meaning that if we have a mass here which is attached to a spring like this, so if we put the mass in this direction, our restoring force always acts in this direction. It is directly proportional to the displacement from the mean position. So it is opposite in direction to the displacement, meaning if you displace it this way, the restoring force acts in this direction. Hence the need for the negative. So if we add those two forces together, we are going to have this expression. And from kinematics, A is equals to x double dot and V is equals to x dot velocity. If we substitute those two together, we are going to have the equation for our damped harmonic motion to be equal to this. So mx double dot plus bx dot plus kx is equal to 0. So we divide through by m, we have the next equation here, of which we can, if we let gamma to be equal to p over m and omega naught squared to k over m, we are going to have this as an expression. Now this is a differential equation which we can solve by first of all finding the auxiliary equation. This is going to be the auxiliary equation. So we are putting that by saying d over dt square is equals to the square, and d over dt is equals to m. This is m square. So this becomes our auxiliary equation, which we can solve by using our formula method of solving quadratic equation. Our answer for m becomes this. So two distinct rules. So the general solution of our differential equation should be given as this. So this is the first rule, alpha. This is the second unit, beta. So to substitute it from here by letting alpha to be negative gamma over 2 plus, so negative gamma over 2 minus, this is beta. So this part is for beta and this part is for alpha. Moving on, we are going to let delta. If delta is this, it means the equation we saw just now can be compressed to give us this. Very factorize this expression out. So we want to see some cases of damping. The first case we want to see is our lightly damped system. So for our lightly damped system, we have the amplitude of the motion to progressively become 0. It approaches 0, meaning that it doesn't just go to 0 immediately. It decreases gradually. And for a light damping system, we have that omega d, which is our damped angular frequency, to be equal to this expression. This is our damped angular frequency. And for a light damping system, k over m minus v square over 4x square must be greater than 0. If we solve this inequality, we are going to have p to be less than 2 root mk. So it's very easy to solve by saying k over m is greater than b square over 4m square. So if you take a cross multiplication of both sides by m cancelling 1m from here, you should have that you should have v square is less than 4mk or mk. of course, you can take square root of both sides, and B is equals to square root of 4mk. B is equals to square root of 4mk, mk please. Then you take square root of 4, get 2. So that's how we arrive at this expression. So anytime our damping force constant is less than this parameter, it means that the case is a light damping or underdamping system. So we can let delta to be negative, to be I times omega d. We got this from here by saying we can rewrite this expression to be square root of minus 1 times negative gamma square over 4 plus omega naught square. So square root. So square root of negative 1 is I. That is how this I came about. Then we know that omega d is this expression, is omega d. So we can say this. If we substitute that back into this expression for x, I'm going to have this expression out, of which you can compress the mathematics. This gives us this, and this is our resulting solution for a general solution for a light damping or the damping system. It's just basically mathematics that we did the trigonometry conversion. Let's see the second case is a heavily damped system or overdamped system. For a heavily damped system or overdamped system, the amplitude of motion goes to 0 immediately. So it's very, very damped. So our damping force constant will always be greater than this parameter again, our damping force constant. And notice this is our general solution for the case of a heavily damped system. So the last one we'll see is a critically damped motion. In critically damped motion, this is always true, and if that is true, we have this. Why? Because you know our auxiliary equation m was equal to negative gamma over 2 plus or minus square root of gamma square over 4 minus omega naught or square. So if that is m, if this is true, then m should be equal to negative gamma over 2 only. So this becomes the general solution for critically damped motion. And k over m minus b square over 4m squared is equal to 0. Note b is equal to 2 root mk for a critically damped motion. So this is just a little diagram to show us how the amplitude decreases gradually for these study cases. So they are worth looking at. Go to the amplitude and energy. The amplitude of and energy of a damped system. For a damped system, the amplitude is given as this. So this is the damped amplitude at any time, and this is the initial displacement or initial amplitude. So if you we can move on to the energy of the system. So the energy of the system is the sum of the find the kinetic energy and find the potential energy and sum them together. So let's use the case of the lightly damped system. So let's use the lightly damped system. So these are expression for x of t. So these are expression for x of t. This becomes x squared. Simply square both sides. So if we square both sides, we'll have this expression for x squared. So our potential energy, first of all, make this approximation. Don't forget that for a very lightly damped system, then omega d should be approximately equal to omega that. So potential energy U, which is half kx squared, should be equal to this. So we just substituted for x squared this expression. Now let's get our x dot so that we can find our kinetic energy. X dot is gotten by using the product rule. If y is equal to uv, if y is equal to uv, then y dot should be u dv plus v du. So that's the product rule that I used for this expression here. So we can have our x dot square to be this, and of course we can expand the square and have this. So we need to make another approximation too, that gamma is always much less than omega d. So gamma is almost much less than this, and gamma is always much less than this. Then can absorb this and absorb this into the equator because they will be much smaller, so they will be much more smaller than this. So if you observe that, you're going to have this expression finally. So we use the approximation sign here to show that our kinetic energy is approximately equal to this. And of course, if we add them together, this becomes power energy. Everything here is equal to 1 from mathematics, and this is the energy of our motion. Our initial energy can be gotten when t is equal to 0. So if you make t to be 0, we have our initial energy to be given as this. The energy per unit mass can be gotten from this. Then we also have our damping power. Then we move on to the method of describing a damped oscillator. First method of describing a damped oscillator is a logarithmic decrement. So the logarithmic decrement is the parameter used to measure the rate at which successive oscillation amplitude dies away. So that's the meaning of method of describing a damped oscillator. That's the first method. So imagine we have oscillator that's decreasing in amplitude like this. So this is the first amplitude A1, this is the second one A2, so this is the third one A3, third amplitude. So our logarithmic decrement is always the log of A1 over A2 and so on and so forth as our logarithmic decrement. Then the next one is our Q factor. So our Q factor is just a parameter used to measure the rate at which energy decays in the system. So this is our method of describing again. So we wrote it here. So let's move on. So have our Q for our quality factor to be equal to this, omega d over gamma, which is equal to 2 pi over delta. So the next one is our relaxation time. So relaxation time is just time taken for the amplitude to decay to 1 over e of its initial value. So this is our expression for the damped amplitude at any time. So the time taken for a naught to be equal to, for a naught the original to be equal to a of t, for a naught to be equals to e to the power of -1 its initial value. So the time taken will be the relaxation time, and if we make it subject, it's giving us 2 over gamma. And from here we can also have our damped time to be half our relaxation time. So if you say that, it means our damped time CD is 1 over gamma. So let's solve some problems on this damped harmonic motion. So the equation of an oscillation they give us is giving us x of t is 5 exponents negative 0.2t sine pi over 2t. So to calculate the natural angular frequency of the oscillation and its period, so that's our question A. So by solution, we're given this expression and we can recall this. So if we compare, you know that x naught is here, x naught should be 5. So first of all, x naught should be equals to 5. So let's say they are measured in, let's use the SI units, it's measured in meters. So x naught is equals to 5 meters. So we can also compare again by comparison that 1 over 2 gamma here should be equals to 0.25. Negative is there, cancels. T is here, it cancels. So 1 over 2 gamma is 0.25, and of course gamma should be 0.5 and we cross multiply. So again, we can compare and you can see that this is our omega d. This is our omega d here. The cosine and the sine doesn't really matter. So omega d is equals to pi over 2. And since they asked us to find our natural frequency, our natural frequency can be given by this. First of all, this is our damped frequency. So since we know damped frequency and gamma, we can find our natural frequency by making it subject. Make it subject from this expression, have this expression. And of course, this is our damped or natural angular frequency after substituting the parameters for omega d and gamma squared. So this is it. So this is you calculate the period. The period t for this frequency, the period is 2 pi over omega naught. So on your own, you can put the parameters for omega naught and for pi and give us what you get. So for B, what is the initial energy per unit? So we can get our initial energy per unit mass from the formula we know before. Initial energy per unit mass is here. Also asked to calculate our damped time is here. We've calculated it already. Then we are asked what type of motion is this. So I've said it that in a lightly damped system, we have that K over M is equal to, not equal to, K over M is greater than B square over 4M square. So this can also be transcribed to omega naught square greater than our gamma square over 4. So, and in this question, you see that omega naught square is greater than gamma square over 4. Of course, omega naught was 3.12, if I'm not mistaken, and our gamma was 0.5. So if you solve those two expressions, you see that omega naught square is greater than gamma square over 4. So the motion is lightly damped. That's the meaning. So our quality factor Q is given by omega d over gamma, which we got as 3.14. So moving on to problem 2. So this is our second problem we're given. If you do like mass, a 250 kg mass, like I'm not mistaken, mass moves at the end of a spring with the force constant K, 0.2 kg please, and the initial displacement is 3. The damping force is this. Acts on the mass, we are asked to calculate the magnitude of the damping force constant. So we can recall that our damped amplitude at any time is given as this. So if we substitute for A naught and A of t, how do we get 0.1 and 3 here? If you remember, our initial displacement is here, which is 3, and we are asked to find the time for which the amplitude of the motion A of t has decreased to 0.10. So that's what we are finding. So we are looking for B. So if you substitute for A naught for A of t for M and for t as 5 seconds, B is this. So we can do mathematics by taking logarithm of both sides, lane of both sides. If we take lane of both sides, first of all, from here we are going to have 0.1 over 3 is equal to exp of negative 5b over 0.4. So that's me. And of course, again, we'll take lane of both sides. Lane of 0.1 over 3 is equal to, lane we always cancel exponents. That's why we have negative 5b over 0.4. So that's why we have it. So if we do the mathematics from there, our B should give us this answer. So moving, and also have problem 3. So you can pause this video and try this problem and see if you can attempt it before checking the solution. So for my own solution, again, we are asked to calculate the time taken for the amplitude to drop to half. So it means that A of t is half A naught. If A of t is half A naught please, then it means A of t is equals to 0.5. So 0.5 A naught. 0.5 A naught. So we can put it here. So it means that before we approached here, we're already having 0.5 A naught is equals to A naught exp and what have you. So A naught can cancel A naught from here. So we have 0.5 is equal to exp times this expression. So please, it is 70 we were given. So this should be changed to 70 and not 0.07. So finally, our time is going to be equal to 4.5